the DevOps concept actually develops about two different duality of the reality we face today in modern development applications. That one part, if you need to code things and do it as fast as you can, and the final product needs to be as correct as possible. And on the other hand, you have to deploy this code you are writing, right? So today we're going to focus on the deployment part. This is all about the infrastructure, right? Your code needs to run somewhere. Your code needs some RAM and CPU and whatever to actually be useful. And your job as the infrastructure provider is to allow that to happen, right? So let's think a minute about how this is typically done in the old kind of way to do it. You basically do this in 4 stages. The first one is allocation, then provisioning, deployment, and finally management, right? So let's talk a little bit about each one. Just if something is not right, please feel free to ask. First, we need to allocate the resources we're going to use, right? These usually involve like a lot of designing and planning. You have to do a lot of networking and budget and actually buy the stuff and find a rack and put the thing in place and connect everything. This usually used to take about a few months, maybe. So in the past, you had to really think about how you will do this in advance, right? So it was kind of hard to design this for spikes in use of the application. So you usually end having too little capacity or too much capacity. It was like a kind of a problem there. Once you have the actual thing, the server in place on the rack and the network and everything, then it's obviously not useful outside the box. You need to provision the box. The typical way to do this is like, you install any OS you're going to use, and usually you connect to the box some way, and then you start to type a lot of commands, right? You hardening your network environment and do firewall configuration, and then usually you already know beforehand what is the purpose of that box. It is going to be like a database server or whatever, and then you usually do something to that purpose. At the end, you end up working a lot on a purpose-specific boxes. You have a lot of servers, and this is my DNS server, and this is my file system, and so each box serves a single purpose. Over time, we start to see that this was not a really scalable approach. So a lot of cool tools started to emerge around this problem. You maybe are using today something like Chef or Puppet or Ansible, something like that. So it is better than typing a lot of commands over SSH or something like that. But also each tool has its own overhead. You have to learn how to use the tool. You have to maintain a couple of components there and keep everything in place, and maybe you do the recipe or the playbook for Ansible or whatever, and then you have to really test things out. So it's better, but it's still kind of a pain to do. If you're doing this in a couple of boxes, I know 10 to 20 boxes, it's okay. Once you have like 500, it starts to get like a really big problem there. And also, typically, once we have like all the little details very well defined, we develop like an emotional attachment to it, and then you have like, you put cute names to your servers, and you care for them like deeply, They can wake you up in the middle of the night, and you're going to be like, something is wrong there. So that's cute and all, but in reality, it shouldn't be that way. So then once you have everything, everything is in place, everything is configured, everything is running. Okay, now let's add my code to the mix. I have my application. I'm going to install this on this very carefully configured server, and suddenly things don't work, and then you start to have this like, it works on my machine like kind of moment there. So have this happened to anybody here? Yeah, sure, more than once, right? So it's a pain, and it usually is because applications or old applications are not single units. They depend on a lot of different things, libraries and settings and whatever. And then if you miss one little detail, it's going to hurt down the road. So this part also involves a lot of time and thinking into doing it, right? And of course, once you have this your code in place and it's finally working the way you wanted, you spend about a week in this by this point. Now you have to monitor everything, right? You have to keep an eye on things to make sure everything stays in a good health. Also, for example, over time, things are going to need attention from your side. Maybe a package or security problem emerge, and you need to patch something. You need to install an upgrade, and the typical way you do this is whatever. Let's talk about Linux just for an example. But whatever the distribution you're using, you usually upgrade package by package. Maybe you're using OpenSSL, and then Heartbleed or whatever bleed comes out. And then you need to patch things up, and then Nginx stop working, and then your code stop working, and then so you have to handle all those kind of things. Also, some packages, let's say a database, for example, requires not only like the dependencies and the binary itself, but also maybe some configuration. So you have your very carefully designed text file on etc, and then when you upgrade, maybe the new version have like a problem there, and then you have to merge your file with those changes, and also every once in a while, typically, I don't know, some years, 2 years, almost 3 years, you have to upgrade like everything, there's a Debian 9 or Red Hat 5 or whatever, and then you have to do everything again. OS upgrades are really painful. I don't know, I'm sure all of us have dealt with this in one point. So it's such a pain that you typically avoid it as much as possible. So you end up having servers way old, and that's a problem also. That's a security problem. So the whole point of all these different stages is just to keep your infrastructure in a consistent and operational state. The thing needs to work, needs to be useful for what you are trying to run over there, right? So with all this in place, I mean, let's think about it, just for a second, and try to define what a better way should look like, right? So, for example, what a location should be. This part, the cloud, has us covered there. What typically take months to do, thanks to the cloud and specifically to virtualization, we can now allocate 1,000 nodes in minutes instead of months. Of course, once you have 1,000 virtual servers, you need to manage those and provision those and all that kind of thing. But for the allocation part, the cloud pretty much is here to stay. We can already agree on that. Then it comes the provisioning, right? The thing that you have to make your new booted box usable, right? I need to be able to run things here. So a better way to do this, it should be like the provisioning should be general. I mean, it should be the same process for every single node in our system. It shouldn't be like a different recipe or playbook for each single purpose box, right? We need to move away from the single purpose design. Also, it should be simple, minimal, and fast. I mean, if we can do this without any extra tools, Beam, Puppet, Chef, or whatever, it would be great. Not because these tools have anything wrong with them, but basically because less is more in this approach. So if we can do this as fast as possible and without any additional requirements, it would be great. And also, it should be automatic. As soon as I boot the machine, it should work. I don't need. I didn't need to do like anything else to do it, right? Just like as soon as it's up and into the system, it's usable right there. And then it comes the deployment part. And this involves our code, our application, whatever we're trying to run on these machines. And the basic idea here, the new hot message containers, the new old hot message containers. Why? Because the containers allow me to pack my code and my application with all its dependencies in one single unit. So I don't really need to care anymore about if I'm going to run this on my machine and I have OpenSSL 108, whatever, and now I'm going to move this to the server and it suddenly stopped working. Now with containers, that stopped being a problem because I can pack my code with the version it uses of OpenSSL and whatever other runtime or libraries I may need. So the basic idea behind the containers is that I can pack once my thing and it should run like anywhere. Well, Linux right now, but it should run on whatever distribution I'm using, right? So as long as it has like a modern kernel version, it should run. And then it comes the management also, you know, management where we were discussing patching things and keeping the OS up to date and all that kind of thing. In an ideal world, it should be done also automatically. I shouldn't really need to think about this, you know, like the machines will take care of themselves and update as much as needed and simply boot and keep usable, you know. So that will be like an ideal design or world. So the next question will be how to do it, right? Because that's like the interesting part. So here we need to think about things a little bit differently. So for instance, the infrastructure, we need to think of it in terms of the resources we're going to use. We need to stop thinking in terms of servers, of individual, virtual or physical servers. We need to think about our infrastructure in terms of CPU cores and gigs of RAM and data storage capacity and all that kind of thing. So as we said, the cloud, we need to do this using cloud as much as possible because it allows us to be flexible in our capacity. The resources, we need to think about the things they provide for the applications to run instead of each different server. Also, there's I don't know, have you heard about some minimal OS distribution? There are a lot of couple of new Linux distributions being developed right now. There's a Snappy from Canonical. There's Atomic from Red Hat, and also CoreOS, for example. And the basic idea is this new OS design is thought from the ground up to be useful in this kind of approach, in this kind of architecture. So for instance, I don't have a package manager. I can install anything on the box. I can do apt-get, whatever, you know, I can do it. So also the main system is read-only. I can really write anything to the. I can store my configurations on etc, for example, something like that. So, and the upgrade process is an atomic upgrade. Usually use the Omaha architecture. The idea is the system boots in a dual partition setup. So let's say A and B, and the system boots on A, and periodically it will check for updates. And once a new version is found, it will download the version to the B partition, and then at some point, based on our configuration, it will shut down and reboot on the new partition. And it will just boot on the new version. And then now I'm running the new OS version. You know, I don't really need to think about it. I don't really need to do anything extra. Just I'm going to set, you know, each Sunday at 1 a.m. check for updates. And if there's one available, go for it, right? And the system will do its thing on its own. I don't really need to think about it. And since I'm not running, I'm not storing any package or configuration in it, I don't really care if the whole thing just gets wiped out and gets burned or whatever. I can just continue using it as it is. And as we said, containers are the new way to package our application and to run it on this kind of system. So the basic idea behind it is scalability, because logically it's easier to think and to manage one big cluster than 500 different nodes. Okay, so let's say you have hundreds of nodes and they just pull the resources together. In a way, it's like the opposite thinking to virtualization. In virtualization, you have one very big box with a lot of resources, and you divide this into independent units to do a more efficient use of the resources, right? And in a cluster setup, it's the other way around. You have a lot of different independent units, let's say boxes, servers, whatever, and you want to pack everything together and pull the resources together in one big, unit, and then just manage that one big unit. Don't you stop thinking about I need to provision and manage 1,000 servers, So it's logically simpler to do it that way. And then, of course, once we have a cluster, we need some tool to be able to manage the whole thing. And there's where Kubernetes comes in, right? Because Kubernetes is actually just that, a cluster management tool, right? So the whole idea is once we have a cluster, we install Kubernetes on it, and we use Kubernetes to run our code in it. So that's a different approach, because you have to understand you first need a cluster. Kubernetes is not going to build the cluster for you. You're going to install Kubernetes and use it to manage it, but you first need to do the setup yourself. So Kubernetes is packed as a lot of different units. It's not just a one single application that you use. It has just two basic dependencies you need to think beforehand. And one is a distributed storage layer. So basically, Kubernetes is basically stateless, because we said in a cluster setup, every single node can be just be gone any given second, and it should be all right. You shouldn't depend on any single unit being present, So you can rely on that. So it needs to be stateless. So you use a distributed storage, mainly etcd. I don't know if anyone has used etcd in the past. No. We're going to see it in the demo, so it's okay. Also, once you have the distributed storage layer in place, you need a network overlay, because let's say you have 500 different nodes and you are going to run a database and a WordPress image. We're going to do this in a minute. So WordPress needs to be able to contact MySQL, for example. The two containers need to be able to communicate. So you use things like server discovery and all that, but at the end of the day, basically, one container needs to be able to communicate with another one in another different box over IP. So you need to use just the container IP and be able to reach each other, right? So I don't know if you have tried this just with Docker, but usually Docker networking is not that simple. It's a bit of a pain, actually. It's being developed right now. It's been a lot of work is being done in that area, but you need to think about that. So Kubernetes was first used on the Google Cloud, Google Computing Engine, the GCE, and they use a network overlay to provide a flat network space. So basically, you do a lot of IP tables, routing, and all that kind of thing, so that when a container tries to ping or communicate with another container on a different part of the world, whatever, that network packages are wrapped and then reroute and then unpacked and delivered to the container that needs to receive them, right? So for this, we're going to be using another project called Flannel, which is great. And once you have those two dependencies in place, now you can start deploying Kubernetes itself. So Kubernetes, the middle section here are the master components. These components need only to be installed on the node that is going to be acting as a master. You can have multiple masters on a cluster. You should have multiple masters on a cluster. But today we're going to be running just with one master. There you have the API server is the first component you're going to be using. Basically, it just provides an endpoint so I can communicate with the system and do some administration tasks, you know, like list the nodes that are in place or the containers that are running, the services, all that kind of thing. So then Kubernetes itself doesn't run containers per se. Kubernetes basic unit of operation, it's called a pod. We're going to look at it. So basically, think of a pod like a wrapper around the container that it provides a few additional functionality to the basic raw container, right? So you send the pod to the API server. You said, okay, I want to run this. Let's say this is my SQL database or my very cool application or whatever. And then the API server gets the pod, and then it uses the scheduler. It's a different component to find it a place in the cluster, right? Because I may include in the pod definition like the infrastructure requirements for this particular unit. Let's say I want to have a 1 gig of RAM and a whole CPU core for myself because I'm super greedy. And then the scheduler is going to look at all the nodes available and find a right place to run that pod. And then the scheduler is going to communicate with the node and said, okay, here's this thing, run it, right? And the thing that is going to catch on the node, the definition, is the kubelet. This is another component. And the kubelet is going to get the pod definition and actually do the work of running the container. And from that point, it will, at this moment, it will just deflect to the whatever container implementation we're using, most likely Docker, but in the very near future is going to be Rocket, for example, which is way better. And pretty much that's it. Once we are in that point, my container is running on that particular node, right? And then the next level of the pods are run on a fire and forget basis. So basically, once that is done, that the whole process we just described, if at some point that pod or that container dies for whatever reason, my application crashes or whatever, Kubernetes is not going to care about it. So we're going to end up with a lot of downtime there. And the reason is we didn't tell Kubernetes to monitor the thing for us and to keep a certain level of containers running, right? So if we want that kind of thing, we need to wrap the pod in another layer, which is called a replication controller. And basically we said, okay, I need at any given moment at least this number of copies of this pod running. And then Kubernetes is going to reflect to this other component, the replication controller, and it's going to keep an eye on things. And if at some point that particular pod dies, it will replicate it and repeat the whole process. And then we have everything running, my container is running, and if it dies, Kubernetes is going to replicate it. But now we need to communicate, right? What we were saying before. Now we need to make the database talk to the front end and to the memcache and to whatever, right? So the last component Kubernetes is going to use for that is the proxy. So basically the proxy is going to use that overlay network component there to allow that to happen. It's going to do a lot of IP tables routing and a lot of very boring stuff, but it will keep running, right? So that's the basic idea behind it.